Welcome back to OCR MEI Further Mathematics B. Today we're doing Chapter 2.1, Introduction to Complex Numbers. So when it comes to complex numbers, it sounds very complicated, but it's really not that difficult to grasp. So let's start by thinking of a number which doesn't really exist, which is the square root of -1. This, because it doesn't really exist, doesn't mean that it's not a thing. It doesn't exist in the real number set, but it is a value on the imaginary number set, which we can denote I, or if you're depends on what purpose and who you're being taught by. You might use J as an alternative value for the imaginary number. For the purpose of my video, I'm gonna stick with using I, which is the old school way of doing imaginary numbers. So given that we now know the meaning of an imaginary number, we can mix and match real numbers and imaginary numbers, so they don't have to be strictly real or imaginary. They are complex. Say I have a value of 1 plus I. This will be a complex number with 1 as its real part, and this will be also 1 because this is technically 1i for its imaginary part. So given that we have a complex number now on our hands with 1 as the real part, 1 as the imaginary part, we can conveniently write this in form of algebra, because math encloses itself. There are basically no loopholes when there's a new concept coming out, because they have to be proven within all fields of math that it doesn't break anything, and turns out that I does everything that we expect it to do in math, and it doesn't break any rules, and therefore it can exist. This is some really old school paper thing that we've proven, but technically I don't actually know how they have proven everything about the complex field, but turns out it works, so we can use it. With that said, normally a complex number will be denoted by a algebra Z, and you can do all sorts of things with complex numbers. You can do quadratics with it, you can model oscillations with it, you can do basically electric circuits with it, and there are all sorts of applications, but for the purpose of this course, we're just getting used to the idea of using I. So given that we now know that complex numbers are just a mixture of real and imaginary parts, we can state different numbers, just different complex numbers. One of the numbers that you must know, which is in your course specifically, is to know that number 0 is equal to 0 plus 0i. Looks either very intuitive or very counterintuitive, because 0 equals to 0. However, you can also say that 0 is nothing in the real part and nothing in the imaginary part, which also means that 0 is nothing. And this is something that you just have to bear in mind, and if you find this obvious, then good for you. Next up, we can actually define this whole thing either as a vector on a 2D field or as a graphical illustration. For vectors, I'm going to talk about that next chapter, so I'm just gonna go over that very quickly. And most importantly, I want you to understand the 2D plane concept. So let's hypothesize a plane of 2D. Normally it will be x and y, but this time I'm gonna state it as the real part, real axes, and the imaginary axes. So you've got two axes now. Different people write their R's and their I's differently. I just write IM because I can't write the curly I. It works anyway. It doesn't really matter as long as you state it clear that it's obvious that it is a 2D imaginary complex plane, which is called the Argand diagram. You should be able to just name Argand diagram as something intuitive. Then, like, it's just a name for this imaginary field. It's called the Argand diagram. Argand. So now that we have defined a Argand field, we can plot the complex number, any complex number in fact. So for 1 plus I, we have 1 on the real axis, and we have 1 on the imaginary axis. So the labels are all just real numbers, and the axes define its reality, I guess. So 1, 1 correspond to this single point. This point will be our z value. So with that, if we take a line from the origin straight to our complex number, this is a straight line, by the way, I just can't draw. We should get a length of, using Pythagoras, square root of 2. And this will be the modulus of z, which is another way of defining a complex number is in the modulus argument form. So modulus is just the name of the symbol 2 lines. I'm sure you've came across that before. And the modulus of a line is always positive by definition. So when you take square roots, don't even think about the negative one, because it doesn't really make sense anyway. With that said, however, we have the argument, the modulus of this complex number. But if you only define the modulus, then technically it can be on anywhere in this circular region, on the edge anyway, because the modulus only defines the length from the origin, and so you should have a circle of radius square root of 2 if you just define these value of z as a square root of 2 within the modulus anyway. To define this single dot, you need to first have a modulus and 2 have an argument. The argument is the angle from the real axis anti-clockwise to the vector going to the z value. So with this said, the argument of z, as I have defined on the Argand diagram, is just theta, and the modulus of z is equal to square root of 2. You want to use Pythagoras for an arbitrary z, by the way. Make sure you use the Pythagoras theorem to get the modulus. Then for the argument for this particular number, it should be a pi on 4, because arctan of 1 on 1 is just pi on 4. Definitely use radians, because if you don't use radians for Argand diagrams, then it doesn't make sense. Argand is defined using radians. So there we go, we have the modulus and argument of this complex number. But how do we go from modulus argument to real imaginary? The way to do that is simply define z as the modulus multiplied by cosine of argument plus I sine of the argument. And this doesn't look intuitive at all, but if you look at the graph, it actually does make sense. So to find the real axes, we have the real part z mod cos theta, and on this diagram we know that z mod cos theta is 1, or whatever this original horizontal length is, and sine theta corresponds to the vertical component of this z, which will give you 1 plus 1i if you plug in the theta and root 2 into this mod arc form. But it works for any argument, any modulus. So this is how you turn a modulus argument into a real imaginary. And before I wrap this video up, I am gonna teach you one more thing, which is called the complex conjugate. For a real and imaginary complex number, they always almost come in pairs. The reason that they come in pairs is because most of the time when we generate complex numbers, they are generated from some real systems that we have hypothesized and made in real life. And in order to be enclosed as a numerical method, if you started without imaginary part, you end without the imaginary part. So if I have a quadratic that is not real, say, let's try this, x squared takes 4x plus 1, I think b squared, no, actually this is the reverse. I want to do this. X squared take x plus 4, and if you know your quadratics, you know that the quadratic formula gives you minus b plus or minus the square root of b squared minus 4 lots of ac, that's 16, all over 2a. And we can see that this is a complex, so we've got a half plus or minus root 15 on 2 lots of I. This is a complex number in pair, and this pair will sum up to a real number. And this has to be the case because it's, again, I need to enclose the system. These parts on the Argand diagram will be a mirror reflection of the real axes, and this pair is called the conjugate pair. I can denote the conjugate pair of Z as, let's see, I'm kind of out of space here. I can denote it as Z star. This is the symbol for a complex conjugate. And on the Argand diagram, the complex conjugate of this Z will have to be the mirror reflection of the normal Z. So this will be the complex conjugate, and this will be -1. So everything on the real axis is the same, but the complex number has flipped sign. This is basically the definition of a complex conjugate. And when you multiply a real number or the original number with its complex conjugate, you get the modulus squared. And this is just definition of complex conjugates that you do need to know. With that said, however, this should be it for the first video on complex numbers. There are a lot to absorb here, but as we go through the remaining few videos, I'm gonna slowly but surely teach more about the complex system, and I'm gonna try to explain how it actually fundamentally works. So next up, we'll try to do a bit of quadratics and actually be able to understand what I've talked about down here with a more complete video. With that said, however, if you have any questions, feel free to leave a comment in the comments below, and I will see you on my next one.